Precalculus, lesson 10.4, I'm sorry, 12.4 in algebra. I'm in chapter 10. Lesson 12.4 called Convergent and Divergent series. This is 12, black pen, there we go. 12.4, Convergent and Divergent series. And here's what we're dealing with. We are dealing with infinite series. So we're talking about taking a set of infinite items, set of an infinite number of items, and adding them up. Okay? So first element plus second element plus third element plus fourth element, where you have an infinite number of elements that you're dealing with. And they can be categorized in two different ways, as either converging or diverging, or as being a convergent series versus a divergent series. So what we have
plugged in there. It looked like suddenly like my microphone might not have been plugged in all the way. I'll have to go back and check. Okay, convergent. We can say this: the infinite series has a sum or limit. By has a sum, we mean has a finite sum. So you might recall in the last lesson we looked at what if you took half of a square plus a quarter of a square plus an eighth of a square plus a 16th of a square, etc., 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 and you did that continuing on to infinity, and it would add up to a finite amount of 1. All right, that's what we mean by convergent, that it does have a sum or it does have a finite limit. And the opposite is what divergent is. So divergent, we could say the infinite series does not have a limit or a sum or limit. Not have a sum or limit. Notice its sum would be quote unquote infinity and its limit would be infinity. Or we would say does not converge, rather it diverges. This is an important component of some topics in calculus, and that's why it comes up in a pre-calculus text. And what else was I going to say there? Oh yeah, the gist of what's going on is this: convergent series, when you go from one term to the next, they're getting smaller at a quick enough of a rate that you end up having a finite sum of all of the terms. Whereas divergent series, even if each subsequent term is getting smaller than the previous, divergent series do not get smaller at a quick enough of a rate to end up having a finite sum. You add up all the terms and it's infinity. Versus convergent, you add up all of the terms and you get some finite value. Okay, so we have two different ways of analyzing whether a series is convergent or divergent. And so we have two tests here. Two tests. One of them is called the comparison test. And the other one is called the ratio test. All right, so with the comparison test, here's what we have. All right, so we'll say that's test 1, test 2. So the comparison test. We can say this: if a series gets smaller more quickly than a known convergent series it is convergent. Okay, if we say convergent series converge because it gets smaller quickly enough, and the series that you're analyzing gets smaller even quicker than that, then it must be convergent. So that's one thing we could say about the comparison test. Conversely, we could say if a series gets smaller more slowly, than a known divergent series, it is divergent. Okay? Again, divergent series diverge because they're too slow in getting small. And if your series gets small even slower than that, then it must be divergent. Then we could also say smaller, let's see, smaller more quickly than known divergent, or smaller, let's see, yeah, smaller more slowly than known convergent, What's going on here? No info. No conclusion. No conclusion. In other words, just because your series is getting small quicker than a known divergent does not necessarily mean it must be convergent. If I give a little drawing here, let's say these are our axes, and we were to graph like dots for each term, and we have, so here's a known divergent one. Let's just say it goes like this. It's getting smaller, but it's taking a little while. Then let's just say we have this known convergent one that is like this. And, keeps on going. That if your series is somewhere here in between, then we don't really have any info. Because if it's going slower, if the yellow one is getting smaller more slowly than the red one, it doesn't mean anything. It's not necessarily divergent, and it might still be convergent. We're not sure. Okay. So the only thing that is telling for us is if the series that we're analyzing, the yellow one, let's just say, is smaller than the red one is convergent, therefore the yellow one must also be convergent. And then conversely, if the one that we're analyzing is taking even longer to get slow than the blue one, which we know is divergent, then the yellow one must also be divergent. Okay? But this middle range in here, we don't know. And that's where sometimes the ratio test will help us more than the comparison test. All right, so we've made reference to these different known convergent series and known divergent series. So what can we work off of here? All right, ones that we know are convergent. We have we have anything of the pattern 1 over n to the p, where p is greater than 1. So an example here would be like 1 over, if we make n 1 and p 2, so that would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus dot dot dot. Okay? So anything that fits that pattern of 1 over n, where n is 1, 2, 3, 4, depending which term you're on, and then p is some power, some exponent greater than 1. That one we know is convergent. And then the other thing that we know is convergent is a geometric series with a ratio smaller than 1. So we could say that would be, well, I'll just go ahead and say here, geometric with absolute value of r is less than 1. In other words, r is between -1 and +1. So an example here might be something like, let's just say we had an a sub 1 of 10 and an r of 1/2. I'll go 1/3. All right. So then what would that be? That would give us 10 plus 10 thirds plus 10 ninths plus 10 27ths, where each term we're multiplying by 1/3. Okay, so any geometric with the ratio less than 1, we are convergent. All right, how about divergent? Divergent. What do we have? One known example is, well, any geometric with ratio greater than 1. So you can say that geometric with absolute value of r is greater than 1. And then something that's called the harmonic series. The harmonic series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot dot dot. This one diverges, which seems slightly counterintuitive because each term is getting smaller, right? 1/2 is not as small as 1/3, and 1/3 is not as small as 1/4, etc. But it's in this blue category here, up above here, where it's taking too long to get small enough to end up having a finite sum. And then one other one that we could give is any arithmetic. Let me say any arithmetic. Any arithmetic. Again, that's one where you're adding the same value each time. And even if what we're adding is 1/millionth, well, if you add 1/millionth an infinite number of times, you are not going to get a finite sum. Okay? All right, so those are ones that we can use to compare for the comparison test. And so the comparison test can be done just looking at the actual values, or sometimes it can be done in a helpful way by converting it to being in terms of n. So let's look at a couple. So this might be like here, example. It'll be like use the comparison test to determine if, convergent or divergent. And let's say we have something like this. Let's say we have 5/3 plus 5/4 plus 1 plus 5/6 plus ... All right. And what you can do with this is you could use your gut to say, well, all right, I'm using the comparison test, so I want to compare it to a known convergent and see if I'm smaller than that. If so, then I am convergent. Or I want to compare it to a known divergent, and if I'm bigger than it, then I must be divergent. And you can use your gut to pick which to test first based on which you think it is. So I look at this and I see something that kind of looks harmonic in the denominator. I'm going 3, 4, 5, 6 in the denominator. That's something that's kind of harmonic. And I have 5s on top. So it's like, I feel like I might be divergent. So let's compare it to a known divergent test, or to a known divergent series. So the known divergent one that we have is 1/2. Oops, sorry, plus that is not, the first one is not 1/2, the first one is 1. 1 plus 1/2 plus 1/3 plus 1/4. And each step along the way here, the first one, the black one, the one that we're testing, it is bigger than the known divergent. 5/3 is bigger than 1, right? 5/4 is bigger than 1/2. 1 is bigger than 1/3. 5/6 is bigger than 1/4. Even if we keep this going out, let's just say we extend this out to the 20th term. The 20th term, so we're at, the first term is 3, the second term is 4, so we need to add 2. So the 20th term, so if we're at n equals 20, then here we're at 5/22, and then here we'd be at 1/20th, and we're still bigger. Even if we went out to the 1000th term, we'd be at 5/1002, and then here we'd be at 1/1000th, and we're still bigger. Okay, so every step along the way, it doesn't matter how far out we go, we're going to be staying bigger than the divergent one. Therefore, this is divergent. Okay, bigger than divergent, you can conclude divergent. Let's do another one where maybe it's easy to see, maybe it's not. I'm going to go with this one. Let's go with, so same thing, use the comparison test. Let's go 10 plus 10/8. I won't reduce just to make it a little bit easier to identify the pattern. Plus 10/27 plus 10/64 plus 10/125 plus ... Okay. Now you might see the 10s on top and think, I think maybe divergent. But, well, if we started to compare it to our known divergent, we'd be comparing it to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And, well, we start out bigger, right? 10 is definitely bigger than 1. 10/8 is bigger than 1/2. 10/27 is bigger than 1/3. But by the time we're here at 10/64, we're smaller than 1/4. 10/125 is smaller than 1/5. So it looks like we're getting smaller more quickly than our divergent series. So that doesn't tell us any information. So let's see if it gets smaller more quickly than a convergent, so we can conclude convergent. And let's see. Now, I could start to compare, but I want to show what this would look like, figuring it out in terms of n. So we have a constant of 10s on top, right? So I can say, well, all right, we have 10 on top. Then what's happening on the bottom? Well, this appears to be over 1. Well, what do I know about 8 and 27? Well, 8 is 2 cubed. 27 is 3 cubed. 64 is 4 cubed. So it looks like what I have going on is 10 over n cubed. 10 over n cubed. Now, when I look at my known convergent series, let's see if there's something I can compare it to. And I see, oh, here I have 1 over n to the p. Let's just say I go with 1 over n squared. 1 over n squared with it, that pattern. So how does 10 over n cubed compare to 1 over n squared? And even though you have that 10 going on, because of the cubed on the bottom, you don't have to go out very far before you can identify that 10 over n cubed is going to get smaller and is going to stay smaller after a certain point. I'm not quite sure which term it is, but it will not take very many terms before 10 over n cubed is smaller than 1 over n squared. And so because of this, you can conclude convergent. So this would be another way to do the comparison test, is put it in terms of n and compare, right? If you went, let's just say you went out to the 100th term. If you went out to the 100th term, so n equals 100, 1 over 100 cubed, that's 1 times 10 to the negative 5th. And if we looked at our 1 over n squared, our 1 over 100 squared is 1 times 10 to the negative 4th. So our times 10 to the negative 5th is smaller than our times 10 to the negative 4th. And it's going to just keep being smaller than our known convergent series. So because it's getting smaller more quickly than our known convergent series, we can conclude convergent. Okay? Hopefully that makes sense. All right, our next test. Our next test is our ratio test. This is our ratio test. And what we do with this is we take the limit as n approaches infinity of a sub n plus 1 over a sub n. Here's what that means. A sub n plus 1 is a representation in terms of n. Well, actually, before I say that, let me say a sub n is a representation in terms of n of our nth term. Right? We had that in our arithmetic and geometric sequences and series lessons. A sub n is the nth term. A sub n plus 1 is the next term after that. And what you do is if you have a sub n as some representation of the term in terms of n, then a sub n plus 1 is just take wherever there's an n and swap in an n plus 1. So let's do an example of what that looks like. Let's go with, I was going to go with, yeah, this one. All right, oop, I have been doing the examples, the question in black and the work in blue, sorry. So let's say use the ratio test to determine, if it's convergent or divergent. And let's deal with this one. Let's say we have 4/3. Oh, I didn't tell you this. If the limit is less than 1, then it's convergent. If the limit is greater than 1, then it's divergent. And if it equals 1, no conclusion. That is important information. All right, so here's the one that we're going to deal with. Let's deal with 4/3 plus 4/9 plus 4/27 plus 4 over 81 plus ... Okay, so what we have to do is we have to figure it out what this is in terms of n. Well, we have a constant 4 on top. And then, well, 3, 9, 27, everything, we're dealing with multiples of 3. And 3 is 3 to the first, 9 is 3 squared, 27 is 3 cubed. So it appears to be that I have 3 to the nth power. So that's what my nth term is. My nth term is 4 over 3 to the nth. So my 8th term would be 4 over 3 to the 8th. Well, what would be the next term after that? The next term after that would be 4 over 3 to the n plus 1. So I can say a sub n is 4 over 3 to the nth. A sub n plus 1 is 4 over 3 to the n plus 1. Now, one way of looking at this is we are multiplying each subsequent term by 1/3. So 4/3, our first term here, 4/3 times 1/3 is 4/9, times 1/3 again is 4/27, times 1/3 again is 4/81. And at that point, if you didn't have to use the ratio test, you could just say, oh, we have a geometric test with the ratio of 1/3, a geometric series with the ratio of 1/3. Therefore, this is convergent. Because any geometric series with the ratio of less than 1 is, between -1 and 1, is convergent. But we're told to use the ratio test. But the reason we have this n plus 1 is, what are we doing each term? We're multiplying it by 1/3, right? If you took this 4 over 3 to the nth, and you multiply it by 1/3, you are multiplying by another 3 in the bottom here, right? Well, 3 to the nth times 3, what do you do to an exponent when you multiply by the same base again? You raise it by 1. So we go from 3 to the nth to 3 to the n plus 1. That's what's going on. But the ratio test, we need to find the limit as n approaches infinity of our a sub n plus 1, so that's 4 over 3 to the n plus 1, over your a sub n, 4 over 3 to the nth. Okay, well that is equal to the limit as n approaches infinity. Let's invert and multiply. So we have 4 over 3 to the n plus 1 times 3 to the nth over 4. Okay, I took this denominator, inverted, and multiplied. Okay, what can we do now? Well, my 4's cancel, right? And so I could rewrite this as the limit as n approaches infinity of 3 to the nth over, now what did we just identify? That 3 to the nth plus 1, well that's the same thing as 3 to the nth times 3, right? Because if you did 3 to the nth times 3, you raise the exponent by 1, and so that gives us 3 to the n plus 1. So 3 to the nth plus 1 is the same thing as 3 to the nth times 3. That's the same thing. So then at that point, my 3 to the nth and my 3 to the nth cancel, and I'm left with what the limit equals, which the limit equals 1 over 3. That's what I'm left with. So because the limit is 1/3, I can conclude convergent, because the limit is less than 1. Okay? Because this is probably a little bit tougher for you to get a feel for than the comparison test. Let's do one more. And let's see one. Let's do one like. No. Sorry, I had a couple things picked out, but then I changed my mind about one or two things. Yeah, there's one like that. You have a little bit of factorial that can come up in this. So I want to make sure that you get a feel for that at some point. Yeah, let's see what happens here. Let's say we have, I'm going to actually make it up in terms of n first. I'm going to go with n factorial over n squared. So what that would look like when n is 1. So factorial, n factorial is n times n minus 1 times n minus 2 dot 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 times 3 times 2 times 1. Assuming that you're starting with an n that is big enough to make that happen. So 5 factorial is 5 times 4 times 3 times 2 times 1. Okay. So what that would look like is 1 factorial is 1 over 1 squared. So that would be 1 plus 2 factorial. So 2 times 1 over 2 squared plus 3 times 2 times 1, times 1 over 3 squared plus 4 times 3 times 2 times 1 over 4 squared plus dot dot dot. All right, so we have it in terms of n. Let's see what happens when we use the ratio test. So we're going to find the limit as n approaches infinity of, so the n plus 1th term is going to be taking my original, but plugging in n plus 1 where there's an n. So that's going to be n plus 1 factorial over n plus 1 squared over n factorial over n squared. Okay, that's the same thing as the limit as n approaches infinity. I can invert and multiply n plus 1 factorial over n plus 1 squared times n squared over n factorial. Well, what would be n plus 1 factorial, but n plus 1 factorial we could say is the same thing as n plus 1 times one number down from that, n, times one number down from that, n minus 1, etc. Well, what's that but the same thing as what's n times n minus 1 times n minus 2? That's n factorial. So n plus 1 factorial is the same thing as n plus 1 times n factorial. Hopefully that makes sense. You can rewind and listen and watch once or twice more. Okay, so then I can rewrite this as the limit as n approaches infinity of, and I just identified my n plus 1 factorial, I can say is n plus 1 times n factorial, right, over what's going to be n plus 1 squared, but n squared plus 2n plus 1, right, times n squared over n factorial. Okay, my n factorial, oops, I wanted red for that, but this is okay. My n factorial and n factorial cancel. So what am I left with? I'm left with this n plus 1 times an n squared. What's that going to give me on top as far as the highest power of n is concerned? I'm going to have an n cubed, right? This is going to be n cubed. I guess I can go ahead and multiply this out. So this is equal to the limit as n approaches infinity. What do I have on top? N cubed plus n squared. N cubed plus n squared over, what am I left with on bottom? N squared plus 2n plus 1. I have an n cubed on top. That's my biggest. I have an n squared on the bottom. That's my biggest on the bottom. As n gets infinitely large, what we can say here is dne, which is does not exist. It's another way of saying that the limit is infinity. But rather than saying the limit is infinity, because infinity is boundless, so it's kind of doesn't make sense to say something is infinity, because infinity is not a thing that something can be. Infinity is something that something can approach. Yeah, so we can say the limit does not exist. That's another way of saying kind of like the limit is infinity. So what would we conclude? Divergent. Divergent. Because if anything, if a limit greater than 1 is divergent, this is like greater than 1 on steroids. It's so big, it's not even a value, right? It's not 1, 2, 3. This is a limit of infinity, essentially. Okay, so that is that lesson. You have a few of using the ratio test, some of using the comparison test, a couple, 1 or 2, where you get to pick which test to use. And that's that. Sorry, this one is a little bit longer. This is just a topic that it takes a little bit of time to get through. All right. Hope you're doing well. I'll see you next time.